kind of remembered how to do long division. Fabulous. Okay, so the way that you do long division, you would divide the divisor into the dividend unit by unit. So 6 cannot go into 5, so we try 53. How many times can 6 go into 53 evenly? 8 times. So we would have 8 up here, and then we would multiply 6 times 8. Well, 6 times 8 is 48. We would subtract 48 from 53. That would give us 5. Then we would bring down the 8 and repeat all of those steps. Divide 6 into 58. How many times does that happen? 9. And then 9 times 6? 54. We subtract. When there's nothing left to bring down, yes, you might have done decimals, but we're going to actually leave it as remainders today, oddly enough. So you would say something like remainder 4. Okay? Now, we don't leave the R4 when we're writing it in polynomial notation. You can actually write it as the quotient, 89, plus the remainder divided by the divisor. So the remainder was 4. The divisor, or the thing I'm dividing by, is 6. So this is actually 89 and 4/6, which yes is 2/3, but that's how we would write this. Does that sound familiar? Yes. The steps were, in case you want to write them down, divide, multiply, subtract, bring down, repeat. So that was divide, and then we're going to multiply, but we're going to put the word distribution or distribute next to this because that'll be helpful for later. We're going to subtract, which is add the opposite. We're going to bring down, and then we would repeat. Those are the steps for long division. Now we can do long division with polynomials. Does that sound like something we've done before? Maybe like once in Algebra 2 you did long division. So here we go. Long division for polynomials. We're going to take the dividend, which is the bigger part, or the numerator, and put it inside the little house. This will be 2x to the 4th minus 3x cubed plus 5x minus 1. And we are going to divide it by x minus 2. All right. The same steps apply. We are going to divide, multiply, subtract, bring down, repeat. What did I forget?
The number that we use for, like, because it's like, how do I explain it? That 2x4 and then 2x3, it's like missing like 2x2.
Amazing. Thank you for finding my mistake. Yes, you would put a 0 there. We do have to put a number for each like decreasing term. Thank you, because I forgot. Every single time if there's a missing term, essentially, you put a 0 there. Okay. Now we have a binomial, so 2 terms. 2 terms can never divide into single 1, so you're actually going to start over here, just like we scooted over 1 in the regular number example. But all you're dividing is the first term by the first term. How, if you divided 2x to the 4th by x, what would you get? 2x to the 3rd. So that again was 2x to the 4th divided by x. Don't worry about the second part just yet. The second part, that minus 2, comes into play whenever we multiply. We're going to multiply 2x to the 3rd times x and 2x to the 3rd times negative 2. So 2x to the 3rd times x, that's 2x to the 4th. And 2x to the 3rd times negative 2, that's negative 4x cubed. I have distributed what's on the top to both parts of the binomial. Do we see that? So we have divided, we have multiplied. The next thing we do is subtract, but you're going to make sure you subtract the whole thing because it's a binomial we're subtracting. That means we're subtracting both terms. So a way to make this easier for you is to change everything to the opposite. Subtracting is just the same like adding the opposite. So I change this to a plus, this to a minus, this to a plus. Change all the signs. The first stuff should always cancel out. If it doesn't, you've done something wrong. But we have 2x to the fourth and negative 2x to the fourth, so those will cancel. We have negative 3x cubed plus 4x cubed. That's 1x cubed. We have divided, we have multiplied, we have subtracted. What do we do next? Bring down. So we're going to bring down this 0x squared. Then we repeat. You're dividing only the first term by the first term. What is x cubed divided by x? X squared. Okay. Now I multiply that term by the binomial. X squared times x is x cubed, and x squared times negative 2 is negative 2x squared. Again, I am taking this number and multiplying it by these two, distributing it to both. We divide, we've multiplied. Next thing we do is subtract, which is just like adding the opposite. So to ensure that I actually subtract both terms, I put it in parentheses and change all of the signs so that I'm doing an addition problem. Subtracting is adding the opposite. First terms should and do cancel. Again, if they don't, something's wrong. And then 0x squared plus 2x squared, that's 2x squareds. We bring down, we repeat. Divide the first term by the first term. 2x squared divided by x is 2x. We multiply 2x times x minus 2. That's 2x squared. And 2x times negative 2 is negative 4x. But all of that we are going to subtract. Subtracting is adding the opposite, so we can change all of the signs. The first terms should and do cancel. And the second terms combine together. That's 9x. We bring down. And deep breath because there's nothing left after this one. So this is the last round. How do you divide 9x by x? What do you get? 9. Then we multiply. 9 times x is 9x. 9 times negative 2 is negative 18. I'm going to subtract all of that. But subtracting is just adding the opposite. The first terms can and do cancel. Negative 1 plus 18 is 17. When there's nothing left to bring down, you have reached your remainder. And just like we did in the first example, you can write your remainder on the end of this quotient as the remainder divided by whatever you're dividing by. So right here, this is my remainder. When there's nothing left to bring down, if you have a number other than 0, that is your remainder. Woo-wee, long division. How do we feel?
I hate it.
I hate it. Okay. It's a lot. So it's a really nice thing that when you are dividing by a term that looks like x minus c, you can also use something called synthetic division. Does that sound like something we've heard of before? Nah. Synthetic division. Here are the steps for synthetic, which I want you to notice. These are the same math problems. So we're going to hopefully end up with the same answer, right? Because we're doing the same thing. The steps for synthetic division are bring down, multiply, add, multiply, add, on and on until you get to your remainder. The way that you set this up, there will be some number k. Sometimes books use the number c. And the L goes backwards this time. And all you have to do is list out the coefficients of your dividend. But again, if you're missing a term, which we are, we put a 0 in that spot. So to set this problem up for synthetic division, we find the number we're dividing by here. It is not -2, it's +2. So we're setting up 2, synthetically dividing with 2, -3, 0, 5, and -1. Where in the world am I getting those numbers from?
From the X at the top.
At the top, 2, -3, a missing term, 5, -1. Bring down. First step, bloop, drop it down, bring down. You multiply the number on the side times the number you just brought down. So 2 times 3 is 4.
2 times 3.
Did I just say that out loud? 2 times 2 is 4. Oh my gosh. It's a Monday.
You had the right answer.
I'm going to pretend that didn't happen.
It's a Monday. That's what the problem is.
Wow, that's embarrassing. Okay. But then once we've multiplied correctly, we add straight down. -3 plus 4 is 1. Then you multiply again. 2 times 1, I can read this time. 2 times 1 is 2. We add straight down. 0 plus 2 is 2. We multiply. We add. We multiply. We add. When you do synthetic division, the very last number you get when you add that last column is your remainder. And then the powers go up from there. So this next term is your constant term, then your x term, your x squared, and x cubed. And if there were more, you'd keep going up each power. So what this means is, and it really does match what we did a second ago, this division gives me the quotient of 2x cubed plus 1x squared plus 2x plus the number 9 plus my remainder of 17 divided by what I was dividing by, x minus 2. And that's exactly what we got when we did all of that long division mess, but significantly faster and with probably a lot less math errors, right? And internal crying. Yes, there should be less of that. So if I'm asking you to divide things, you could go for it with long division. We technically know how to do that. But a lot of times, especially for what we want to do in this class, which is factor these giant polynomials, we'll be finding factors that are x minus c, x minus 3, x plus 5. Synthetic division is going to be very helpful here. But there's one more thing I want you to notice. Okay. Notice down here, this example 3, does this function look familiar? It's the same one. Okay, so I need us to notice that. And what do you notice about this number 2? It's what we were using for k, right? It is plugged in. Let's see what happens when we do this. When we find f of 2, meaning, yes, plug in the 2 everywhere there was an x. Oh my goodness, that's a lot of math. We can use a calculator on this. What is 2 times 2 to the 4th minus 3 times 2 to the 3rd plus 5 times 2 minus 1? Yeah, what do we get? Whoa, what do we notice about this number? That's maybe familiar from other things we've done today. Do you notice this? Where else has there been a 17 today? Yeah, my remainder has been 17 this whole time. What this means for us is that we have this new theorem. It's called the remainder theorem. If a polynomial is divided by some factor x minus c, in this case x minus 2, then the remainder is the same as the function value f of c. Meaning, what we can do to find the remainder, instead of having to do long division, instead of having to do synthetic division, is just literally plug that number in, the value for c or k, and figure out what the remainder is. Okay? That's what the remainder theorem tells us. I would put little stars next to this one. It's going to be, there's like a bunch of theorems today. That's going to be a helpful theorem to remember. It's very short, very small. But on the, we kind of summarize why that's important. So when a polynomial is divided by x minus c, we can find the remainder just like we did on the front with long division. But, ew, I highly doubt you're going to do that. The second choice would be synthetic division. I don't hate that one. I'm going to put a smiley face next to that one. Or with the remainder theorem, which is very easy. That's f of c. I'm going to put a smiley face next to that one. So you kind of have mathematician's choice on this one. If I ask you what the remainder is, you get to pick which version you're going to use to find said remainder. I highly doubt you'll choose long division, but like technically you could still do that. The remainder theorem. Mathematicians are lazy. We shorten everything. THM is the shortened for theorem. Just got rid of all of the vowels in the word and the R. But what's cool about relating these factors to remainders, when we divide two numbers and the remainder is 0, then the value we divided by, as well as the quotient, are called factors. And this works for numbers as well as polynomials. For example, if 20 is divided by 5, the remainder is 0, because 5 divides 20. 5 is called a factor of 20. So if a polynomial has a remainder of 0 when you divide it, then the thing you're dividing by is a factor. So instead of having to factor with like guess and check, for these more complicated polynomials we'll be dealing with, not quadratics, we're doing cubics and quartics and degree 5 polynomials, we're going to want to use this factor theorem to be able to find all of the factored forms of our polynomials. And the factor theorem right here just restates what we said in the little blurb. For a polynomial function, this number c is a 0 if and only if x minus c is a factor. So we can check our remainders, make sure remainders are zeros to decide if things are factors. But there's a lot of related things going on when you get to factors and zeros in regards to functions. So all of the following statements are the same thing. If we know one of these, we know all 5 of them. We would say x equal to c is a solution. So the number c is a solution, also known as a root of the equation f of x equal to 0. And if that's true, then when the function is divided by x minus c, the remainder equals 0. So if you get a remainder is 0, it's a factor. We then also call c a 0 of the function, which then means that at the value c, that's where the graph crosses the x-intercept, or the x-axis, if that c is a real number, because it could be an imaginary number, which we'll deal with later. And x minus c, that little thing in parentheses, is considered a factor of f of x. If you know one of these 5 bullet points, you know all 5. They're all related, which is why it's so important to know these factors, which means I know my zeros, or know the zeros because it means I know my factors. All of these things are related. So, for example, let's say somehow you're doing a math problem and you figure out that x equal to 5 is a 0 for some function. What does that mean a solution or root of the equation is? Also 5. If we know it's a 0, we know it's a solution. When f of x is divided by the factor x minus 5, which is how I would have gotten that 0, the remainder is 0. We also know that 5 is an x-intercept of the graph because 5 is a real number, not imaginary. And we know that x minus 5 is a factor of f of x. I did no math beyond knowing that x equal to 5 is a 0. All the rest of those statements come from just knowing that one little thing. So we get a ton of information about the polynomial if we know its factors or if we know its zeros, which we know one if we know the other. So here's the type of question I can ask you. It asks you to use the factor theorem to determine whether f of x equal to 2x cubed minus x squared plus 2x minus 3 has the factor listed below. I'm going to show you both ways, not long division, because I'm sure you don't want to see that again. But the factor theorem means that I know if I synthetically divide or I use the remainder theorem and I get 0 as my remainder, then they are factors. So we want to see, is x minus 1 a factor of this big polynomial? The first thing we're going to do is synthetic division so you can see what that looks like, so you can make your own choice later. What's the k value I want to use here? 1. Because x minus c is the formula, or x minus k. So k is what I'm going to use on the outside of this synthetic division, and I set it up with just the coefficients of the function that I'm dividing, which would be 2, -1, 2, -3. When I do this division, if the remainder is 0, then it's a factor. Bring down, multiply, add, multiply, add, multiply, add. Remember, that last column tells me my remainder, so the fact that this is a 0 makes me happy because that means it is a factor of the polynomial. I'm just writing that out in words. Since the remainder is 0, then x minus 1 is a factor of f of x. Didn't actually have to show like the final factored form. It was just wondering if it is a factor. So that is one of the ways you can answer this question. If you're trying to determine if something is a factor, check the remainders. So we can use synthetic division, like we did in A, or we can use the remainder theorem, which we will do in part B. See if you like that version better. We need the same sort of numbers though. What's the C value here, or the K value? Is it 2?
Negative.
-2. So the opposite of what's there, because the formula already has a minus sign in it. This time, instead of doing synthetic division, again, because mathematician's choice coming up, you can just plug in -2. If you plug that number in, and when we're done evaluating, we get 0, then it is a remainder. Because whatever the remainder is here, or whatever the evaluated number is here, is the remainder. And thank goodness we have calculators. 2 times -2 cubed minus -2 squared plus 2 times -2 minus 3, which you could do in your head if you wanted, but I know you're going to grab your calculators anyways. What do you get when you evaluate that function at -2? Is that 0? No. So since that is not 0, we could say, since f of c does not equal 0, or f of -2 does not equal 0, then x plus 2 is not a factor of f of x. So this one, part B, we still could have done synthetic division. We would have gotten a remainder of -27 with the same outcome. So it really just depends on what's easier for you and whether or not you have a calculator. Because evaluating that function might be more challenging without a calculator, but the synthetic division, since it's like little quick numbers, might be a lot easier. But mathematician's choice on these. You get to decide how you like to best answer this question. So here's kind of why we went about doing all of this. We have this polynomial, f of x equal to 3x cubed plus 4x squared minus 5x minus 2, and we want to completely factor it. That's a cubic function, which means I can't just sit here and guess and check factor. I'm going to have to use some more advanced skills. So I looked at my graphing calculator, and I found these three things. I know that this graph crosses the x-axis 3 times. So I should be finding 3 zeros. It is also degree 3, which means there are 3 solutions or 3 roots here. Can you tell me what some of those zeros are? Like this one right here, what number is that? -2, right? Which means the factor x plus 2 is a part of my polynomial. Can we tell exactly what that middle one is? It's definitely negative, but can I tell you right away what number it is? So I'm going to be like, hold on, we don't know that one yet. But can I tell you what the third zero is? It's 1, which means the factor x minus 1 is absolutely part of my polynomial. We need to use that information to figure out what the missing term is without using a function on a calculator. So we go to synthetic division. We know that if we divide the polynomial itself synthetically with one of those zeros, like -2, we would get a remainder of 0 out of this. So we bring down, we multiply, we add, we multiply, we add, and multiply, and add. We have a remainder of 0. We knew that was going to happen since we knew it was a 0 of the function. And we repeat synthetic division with the other 0. The other 0 was 1. I repeat. Bring down, multiply, add, multiply, add. Good, I got 0 again. We knew that was going to happen since we know visually that is an x-intercept, so it's a 0. The stuff that I have left is the final factor. This is the remainder. This is the constant. This is the x term. So my polynomial fully factors to what we saw on the graph, x plus 2, x minus 1, and what I got out of synthetic division at the end, 3x plus 1. Here's this 3, here's the 1 that I got out of synthetic division, 3 and 1. Yes. Mm-hmm. So let's say we were going to do another question and we weren't given a graph. So we have no idea where to start thinking for these zeros to be. Luckily, we have something called the rational zeros theorem that helps me find all of the potential zeros for my function. This theorem says let f of x be a polynomial function with integral coefficients. The only possible rational zeros of f are plus or minus p divided by q, where p is a divisor of the constant term and q is a divisor of the leading coefficient. What does that mean? Let me explain. P's and q's come from the leading coefficient, so the first number, the first coefficient, and the constant term, so the last number. I'm going to list out all of the numbers that multiply to the constant number or the leading coefficient, and then combine them by putting all the p's on top and the q's on bottom. Okay, so example 7 and 8 go together. They're the same equation, but we did them in 2 parts. Number 7 says to list the potential rational zeros of f of x equal to 2x cubed plus 11x squared minus 7x minus 6. I don't care about any part of this except for the 6 and the 2. The leading coefficient is 2. The constant is -6. What are all of the things that multiply to 6? 2 and 6. What else?
1 and 6.
And 1 and 6. Sorry, I think I just said that back. 2 and 3, 1 and 6. Those are the things that multiply to 6. So there's all the list of factors for P. What are all the things that multiply to 2? 1 and 2. Okay, small list. We love a small list. So we are going to combine these by putting all of the p's above all of the q's. Our list of potential rational zeros, that's what PRZs, potential rational zeros are plus or minus 1 divided by 1. So I'm taking 1 from the P list and 1 from the Q list, plus or minus 2 divided by 1, 2 from the P list, still on 1 from the Q list, plus or minus 3 over 1, plus or minus 6 over 1, plus or minus, yep, we're still going. We're going back. 1 over 2, plus or minus 2 over 2. Do y'all see what I'm doing here? Sort of. I'm taking all of the numbers from the P list and the Q list and combining them with P's on top, Q's on bottom. So it's a big combination of numbers. Whew. That's my whole list. 1, 2, 3, and 6 are both on top of 1 and on top of 2. Do we see how I've made all those fractions? All denominators are 1 with this combination on top. All denominators are 2 with that combination on top. Now hopefully you notice something right here. What is 2 divided by 2? Don't I already have 1 on my list? Okay, so I really didn't need this. And what is 6 divided by 2? 3. Don't I already have 3 on my list?
Yeah.
So I really didn't need that one either. So those are the lists of all potential rational zeros. I know that one of my zeros or all of my real zeros are going to be in that list. So if the question goes on to ask you, again, without providing you a graph and having you not use a graphing calculator, to factor or to find all the real zeros of this same question, all we have to do is test each and every one of those coordinate points to see what the remainder is. That's a lot to do by hand. So here's your calculator tip of the day. You're going to type the equation into your calculator, into y equals, and then you want to look at the table. But you're going to do this in a very smart way. You're going to change the table settings. You're going to go over and change the independent value to ask. So it's going to say auto, and you're going to change it to ask. And then when you go to the table, it will be blank, and we're going to type in all of those potential rational zeros for our list to see which one of them return back to you a 0 as a remainder. We just did the remainder theorem, and those will be our actual rational zeros. So let me show you what I'm talking about. Once we've found all of the zeros that in my calculator are equal to 0, when I type them in on the table, we can then write f in factored form because we know the relation between zeros and their factors. So a 0 being 1 means that the factor is x minus 1. A 0 being negative 6 means the factor is what? Plus 6. And then a factor being, or a 0 being negative 1/2 technically means, and I want y'all to watch, I don't know how well versed in this you are. Technically you could write this, but we don't write fractions as part of our factors. So if you've done swing and divide, what did we do with those denominators? Has anybody done swing and divide factoring before? No. These denominators actually just go bloop right up there. So really, I wouldn't write this as x plus 1/2. I'd write it as 2x plus 1, where the denominator swings forward. Before today, we would not have been able to factor this because you can't just guess and check factor this type of polynomial. We needed additional strength to find all of the places where it crosses the x-axis or has a 0. Yes, we could have put it in a graphing calculator, but we're doing it algebraically, and then we can factor. All right, the big kahuna, are y'all ready? We're going to find the real zeros of this polynomial. What degree polynomial is this? So how many zeros will it have? 5. We would not be able to do this by hand, but thank goodness we now have the rational zeros theorem as well as the remainder theorem and the factor theorem to be able to do this quickly. The first thing we're going to do is worry about all of the potential rational zeros. So I need to combine the numbers 36 and 1 with all of their factors to get this to work. So real quick, what are all of the things that multiply to 36? 6 and 6, 36 and 1, 3 and 12, 4 and 9. I already missed one. And then 2 and 18. Oh my gosh, look at how many things factor to 36. We're going to combine all of them. What are the things that multiply to the Q term, which is 1? Just 1 and 1. We want the leading coefficient, not the degree. That's a good point. The leading coefficient, not the degree. So we're going to have a bunch of combinations of numbers in my list of potential rational zeros. But luckily, the Q, or the bottom, is always going to be 1. So my list of potential rational zeros are as follows. Plus or minus, and I'm just going to do it all in one color so I don't have to switch. I'm so sorry. 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus, I did those out of order, 6 over 1, plus or minus 9 over 1, plus or minus 12 over 1, plus or minus 18 over 1, and plus or minus 36 over 1. We know that in that list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 things, all 5 of my zeros are going to show up. All the real ones, at least. So we go to our calculator. We're going to take this list of potential rational zeros and get a list of actual zeros. So I want you to go through this list and find me the zeros that work. You could have up to 5 numbers that work for real zeros. Let me give you some time to do that. So you're putting the whole thing in the calculator, making sure your table is on ask mode, and typing in those numbers. So just to save you all the struggle, because I know this problem is atrociously large in the number for 36, what are some of the zeros you found that work? 1 and 3. That's actually going to be the only ones from this list that work. And I know you're like, wait a second, Ms. Quigley, you told us we're going to find 5 of them. Some of these might be repeated, and some of them might be imaginary, which we are not dealing with till next time. We are dealing with the real zeros of polynomials today, not the imaginary ones. So what we're going to do to try to write this in factored form, since I know that I kind of didn't find all of the zeros, so I can't just like put them in cute little parentheses like I did before, we're actually going to have to do synthetic division. So what we would do, we'd just start with one of the zeros and synthetically divide the entire polynomial. So we have 1, -7, 19, -37, 60, and -36. Does everyone know where I'm getting these numbers from? Okay, these are the coefficients of the dividend. And we do our synthetic division steps. Bring down, multiply, add, multiply, add. That's not how you add those two numbers. Multiply, add, multiply, add, multiply, and add. We should get a remainder of 0 because we knew that these were going to be factors. You proved that from the rational zeros. So we try the next one we know for sure to keep trying to make this polynomial smaller. So we try 3. Bring down, multiply, add, multiply, add, multiply, add, multiply. Phew, again, we got a 0 as a remainder. At this point, kind of anyone's ball game. Those are the only two things we knew for sure. We could try dividing by 1 again. We could try dividing by 3 again because we know there has to be up to 5 zeros here. Just as a time saver. 3 is a repeated root, so we're going to do it again for 3. Bring down, multiply, add, multiply, add, multiply, add. If that last number wasn't 0, you would know that whatever you chose to try, had we tried a 1, it wouldn't be 0, that you'd have to erase and try again. Oh man, but if we look at this, this is a pretty small polynomial, considering if this is the remainder, that means this is the constant term, the x term, and the x squared term. What I have left is the polynomial x squared plus 4. If I were to try to factor that polynomial, I'd get an imaginary number. Because subtract 4, take the square root of a negative number is an imaginary. So I'm going to stop here for today. And we would know that our factored form is x minus 1, x minus 3. But how many times did x minus 3 show up? So we would give it a multiplicity of 2. And then we have whatever was left before we hit imaginary world. We would not have been able to factor this polynomial without synthetic division or having guesses on what even zeros to try. So we started with the potential rational zeros, found the ones that actually work, and just kind of strong-armed it till we got to a polynomial that we can't factor without going into imaginary world. Now, actually, this last example here, we'll go ahead and do. It's very similar to the homework question you guys asked about. That last question on the homework. It takes the intermediate value theorem and applies it to polynomials, which is exactly what we did on that example problem. If f is a polynomial function and f of a and f of b are opposite signs, so one is positive and one is negative, then there is at least one 0 between a and b, because it has to cross the x-axis at some point. So to show that f of x has a real 0, we're going to use the 2 steps from the IVT from last time. That first step was to show that it's continuous, but we know that for any polynomial, even a quartic polynomial, that they are continuous. So we literally just have to say that. So the function is continuous. That's the first requirement for IVT to stand. The second thing is we need to know the value at the first point and the value at the second point. This one is asking me between 1 and 2, so those are the numbers I'm plugging in. F of 1 would be 1 to the 5th power minus 1 to the 3rd power minus 1. It ends up being -1. And the second number I'm plugging in is 2. 2 to the 5th power minus 2 to the 3rd power minus 1. That's 32 minus 8 minus 1, which is 23. And since the signs changed, since f of 1 is a negative number and f of 2 is a positive number, we know there has to be at some point between them that we hit 0. Because to go from negative to positive, you have to go through 0. That's enough to show that therefore there exists an x on the interval from 1 to 2 such that f of x is equal to 0, meaning I have a 0 there due to the intermediate value theorem.